All right, welcome to The Explainer. So you're getting ready for a big AI system design interview. There's one question that sits underneath almost everything else. How did this model actually learn? See, it's pre-training. That's its DNA. It basically defines what it's going to be great at and, well, what it's going to be pretty bad at. So today, we're going to decode that DNA. So let's just dive right in with the big one. How do you actually teach a machine to understand language? And look, this is not some philosophical question for a late-night debate. This is the most fundamental design choice you're ever going to make. The answer you come up with here, it's going to dictate the model's strengths, its weaknesses, and yeah, ultimately, whether it's even the right tool for the job.
When you really boil it all down, there are two main schools of thought here. Is it better for a model to learn by, say, playing fill in the blanks, where it has to figure out a missing word using all the clues around it? Or is it better to teach it to be a kind of storyteller, always just trying to predict what comes next? These two paths, they lead to completely different kinds of models, and knowing the trade-offs between them, that is absolutely critical for that interview.
Okay, so here's the game plan. We're going to start with the fill-in-the-blanks method. Then we'll jump over to the what's next approach. From there, we'll see how these training recipes lead to the big model families you know. And to wrap it all up, we'll get into the nitty-gritty comparisons you'll need to ace the interview. Let's do it.
All right, section 1, the fill-in-the-blanks method. I love this analogy. Think of it as training a model to be a detective. It gets to see the whole crime scene, all the evidence both before and after the missing piece to solve the puzzle.
Okay, so the fancy technical term for this is masked language modeling, or just MLM. The key phrase to lock onto here is surrounding context. This is huge. It means the model isn't just looking at the words that came before the blank, it gets to peek into the future too. It can see words to the left and to the right of the missing piece. It gets the whole picture to figure things out.
So take a look at this. To figure out that masked word, the model has to connect the dots between what comes before it, the model learns, and what comes after it, contextual representations. This whole process forces it to build this really deep two-way understanding of language. We call that bidirectional. It's not just guessing what's next. No, it's really deducing meaning from the entire context it's given.
And what does this all mean in practice? Well, this kind of training is perfect for any task that needs a deep understanding of the text, not generating new stuff. Think about it for a sec. Things like search, or ranking results, or classifying a document. They all rely on having a super rich representation of the input text. And the classic example of a model trained this way? That's got to be BERT.
Now, back in the early days of these models, especially with BERT, they used another trick called next sentence prediction, or NSP. The whole idea here was to teach the model how sentences relate to each other. You give it two sentences and ask, hey, does sentence B actually make sense following sentence A? Simple as that.
But here's the thing about its relevance today. While NSP was a really important step, a true historical milestone, it turns out it's not as critical as we once thought. Researchers pretty much figured out that models could learn those same sentence-level relationships just from the main masked language modeling task. So having a whole separate step for it kind of became redundant. It's a cool part of the history for sure, but not really part of the modern recipe.
Okay, on to our second big idea, the what's next method. If the first one was a detective, this one is the storyteller. It's not about solving a mystery that's already laid out, it's about spinning a brand new tale.
The technical name for this one is autoregressive modeling. Now, remember our detective? It could look forwards and backwards. This model? Nope. It's only allowed to look in the past. It reads strictly from left to right, and its one and only job is to guess the very next word, or token, based on what it's already seen. That's it. So its whole mission in life is just to complete this sentence, one single token at a time. It's this relentless, constant act of prediction and continuation that makes it so incredibly good at generating text that feels fluid and coherent.
So as you can probably guess, this what's next objective makes these models natural-born generators. They are tailor-made for any task where you need to create something new. We're talking chatbots, summarizing long articles, writing code, even creative writing. If your job is to generate a sequence of text, this is the training recipe you want. And the absolute poster child for this approach? Well, that's the whole GPT family.
Okay, so let's connect the dots. We've got two totally different training recipes, the detective and the storyteller. But how does that one choice at the beginning lead to these huge, distinct families of models we hear about all the time? Why is this one decision so incredibly important?
All right, pay attention, because this slide right here, this is the one you need to burn into your memory for the interview. It ties everything together. Just follow the logic down the rows. The primary goal, are you trying to generate text or understand it? That directly determines the kind of attention the model can use. Autoregressive models have to use causal left-to-right attention. Why? Because they can't see the future they're trying to predict. But the masked models, they thrive on that bidirectional, see-everything attention to build that rich context, and that choice then determines what they're best for. And boom, that's how you get the two big families. GPT for generation, BERT for deep understanding. It's the fundamental trade-off in a nutshell.
Okay, now that we've got that core distinction locked in, let's build on it. We're going to run through a few other key comparisons that an interviewer is totally going to ask about. Getting these terms straight will help you see the entire map of the AI world. First on the list, generative versus discriminative. It's pretty straightforward, actually. Our storyteller models, they're generative. They learn the deep patterns of language so well they can actually create something new. But our detective models, they're often used for discriminative tasks. Think sentiment analysis. They don't have to write a new movie review, they just have to draw a line in the sand and decide if an existing one is positive or negative. I love this analogy. It's the difference between being an artist and being a critic.
All right, next up, foundation versus task-specific models. This one is all about scope. Think of models like BERT and GPT as foundation models. They're the generalists. They've been trained on a massive, diverse chunk of the internet, so they know a little bit about everything and can be adapted for all sorts of jobs. Then, you can take one of those and fine-tune it to become a task-specific model, a real specialist. You can turn it into an expert summarizer or a dedicated code bug finder. It's really just the classic trade-off, a huge general library versus a super-focused expert textbook.
And last but not least, how do these modern LLMs stack up against the old-school methods, like n-grams? Well, here's the simplest way to think about it. LLMs do something called representation learning. N-grams just do statistical counting. What does that mean? An LLM actually learns a rich, nuanced concept of what the word king means and how it relates to queen or royalty. An n-gram model, it just knows that the word king shows up a lot after the words the or a. See the difference? It's understanding a concept versus just memorizing a pattern.
And this brings us to the single most important takeaway, and it comes straight from the source material. If you remember one thing, remember this. When you're comparing models, always start from the learning objective. That's the first principle. That one decision at the very beginning is what quietly dictates everything else, the architecture, the behavior, and ultimately what the model is actually good at in the real world. And that's our deep dive for today. A model's pre-training objective, it really is its worldview, its DNA. It shapes everything. So I'll leave you with a question to chew on, something perfect for your next system design chat. If the objectives we have today create these amazing detectives and storytellers, what kind of objective would you have to invent to teach a model real, genuine common sense? Seriously, think about it. The answer to that question? Well, it might just define the entire next generation of AI.